Something above Earth's fiercest thunderstorms shoots lightning straight upward into space, and scientists finally captured one of the rarest types with crystal clarity. These are transient luminous events, TLEs, and they have nothing to do with the lightning that strikes the ground. They are upward, they are faster than you can see, and they occur in zones where the air is so thin that normal lightning physics breaks down and something stranger takes over. For decades, they were only rumored, caught in brief photographic flashes by accident. Now ground-based high-speed cameras, the International Space Station's ASIM instrument, and dedicated surveys have turned these ghosts into documented physical events. Here is the reality. When a powerful thunderstorm builds a massive charge separation, positive charges accumulating in the upper regions of the cloud and negative charges near the base, the electric field can become intense enough to ionize the air far above the storm top. At normal altitudes, this creates ordinary lightning, a downward strike between cloud and ground. But above roughly 70 to 90 kilometers, where the atmospheric pressure is thousands of times lower than at sea level, the breakdown produces something entirely different. The first category is red sprites. They are massive vertical discharges of reddish light, reaching 30 to 90 kilometers high, sometimes spanning 50 kilometers horizontally. The red color comes from molecular nitrogen emitting at the low-pressure altitudes where the discharge occurs. They last roughly 10 to 100 milliseconds, far too fast for human perception, too brief for ordinary cameras. Scientists have documented them since 1989, but they remain among the most dramatic atmospheric phenomena on Earth. Then there are blue jets, narrower, faster, and more energetic. They erupt from the cloud tops themselves, shooting upward in bright blue channels made of ionized nitrogen and oxygen, reaching 20 to 50 kilometers altitude in fractions of a second. They are much shorter-lived than sprites, and because they occur closer to the storm core, they are harder to observe from the side without being blocked by cloud structure. The rarest and most energetically extreme are gigantic jets, also called blue starters when they initiate near the cloud top. These combine the vertical reach of sprites with the intensity of blue jets, extending up to 80 to 90 kilometers into the mesosphere and lower ionosphere. Only a handful have ever been documented with adequate data. They occur when a storm's electric field is extraordinarily intense, and the upper atmosphere conditions align precisely to allow upward ionization rather than downward discharge. And then there are ELVs, emission of light and very low-frequency perturbations due to electromagnetic pulse sources. These are expanding rings of light, usually red, that spread outward from a lightning strike at the speed of light across the ionosphere at roughly 90 kilometers altitude. They do not travel upward like a jet. They expand horizontally like a ripple across a pond, lasting less than a millisecond. What makes all of these rare is not just speed. It is the specific atmospheric physics required. The storm must generate enough charge separation. The upper atmosphere must be at the right density and temperature. The observer must be positioned correctly. Because these events happen above the storm, they are best captured from aircraft, satellites, or high-altitude platforms looking down at the storm's electrical anatomy. The International Space Station's ASIM instrument, installed in 2018, changed this. It is specifically designed to observe TLEs from orbit with high temporal resolution, fast enough to catch millisecond events, and spectral coverage that distinguishes between sprite, jet, and ELV emissions. Combined with ground-based all-sky camera networks that continuously photograph the sky above storm systems, researchers now have multi-point confirmation of events that were previously isolated anecdotes. In 2023 and 2024, high-speed camera arrays in Japan and Europe captured blue jet initiation with unprecedented clarity, showing not just the discharge, but the exact structural dynamics of how a jet forms at the cloud-top interface. These observations feed directly into atmospheric models that could eventually improve thunderstorm forecasting, because intense TLE activity correlates with particularly energetic storms. The energy involved is enormous. A single gigantic jet can release more than a gigajoule of energy in a fraction of a second, roughly comparable to the output of a medium-sized power station, released in a single upward burst. The particles emitted into the ionosphere can alter local ion density and affect radio propagation conditions, though the global effect is minimal. So why does this matter beyond the visual wonder? Because for all of human history, thunderstorm energy has been observed as downward. Lightning strikes the ground, causes fires, kills trees, powers our grid. But the same storms are sending enormous pulses of energy upward into the ionosphere and mesosphere, shaping atmospheric chemistry, ionization, and possibly affecting climate-relevant processes at altitudes where satellites orbit. The fact that we are just now catching them clearly is partly because they are genuinely rare. Not every storm produces them, and partly because they are invisible to the human eye and too fast for ordinary cameras. The combination of space-based instruments like ASIM and high-speed ground networks has finally given scientists the tools to study them systematically rather than by accident. So here is my question for you. If the most violent storms on Earth are secretly shooting energy upward into space at speeds faster than a bullet, and we have only recently learned to see it clearly, how many other invisible atmospheric phenomena might be happening above your head right now?